Yeah, perfect. Thanks. So I'm pleased to present this joint work on certified program synthesis with my co-authors Yasunari Watanabe, George Pelia, Nadia Polikarpova, and Ilya Sergey. Okay. So imagine that you are a developer tasked with implementing the specification for a list copying program in separation logic. In your precondition, you would have the assertion that you have a pointer, a reference to a singly linked list represented, whose presence is represented by the inductive predicate SLLXS. And in the postcondition, eventually, after executing the function, you would also like to have that same linked list returned and a freshly allocated copy with the same set of elements S and a updated reference that now points to the head of the linked list. And because we're working in separation logic, we have access to this star operator, which represents the separating conjunct, and simply means that the left and right spatial expressions refer to disjoint parts of the heap. Now, the inductive list predicate is defined as follows, with two cases: an empty case when the pointer x is nil and the set of elements is empty, and a non-empty case in which the pointer is non-nil and x points to the head of the linked list and x plus 1 points to the tail. So at this point, any other developer would start rolling up their sleeves and writing a program. But not you. No, you're too clever for that. Instead, you pass this specification to SuSLik, a program synthesizer that is capable of automatically producing an implementation given this specification. And voila, a list copying program. But just then, you're hit with a wave of doubt. How can I trust this result? The synthesizer is written by humans, and so surely a bug in its implementation could cause it to produce incorrect programs. So ideally, what we want is some kind of formal guarantee that the programs produced by SuSLik are indeed correct, i.e. that they satisfy the specifications that were used to construct them. Now let's return. So in this work, we'll be looking at exactly this problem of producing formal guarantees of the correctness of synthesized programs. In particular, we'll be ensuring the correctness of the synthesized programs by means of generating proof certificates. And in particular, this technique relies on using the deductive insight used in the synthesis process. Okay, so now let's just return to this question of trust. Our earlier misgivings arose because the SuSLik synthesizer has quite a large trusted codebase, or TCB. And if we want to avoid this kind of situation, we ideally like to shift the burden of trust from something with a large large TCB to something with a more minimal TCB, such as the Coq proof assistant. And this is particularly fitting for our case because Coq proof certificates are widely considered as correctness guarantees for important theorems and critical programs. Proof certificates. Okay, now we have a problem here because the SuSLik codebase is fairly large, and so it would be rather impractical to actually sit around and try and verify it manually ourselves. But luckily, as it turns out, the deductive approach that SuSLik uses in synthesizing programs means that its approach is rather amenable to post hoc certification. So rather than verifying the entire synthesizer, we can simply extend it to also produce additional proofs, machine-checkable proof certificates that can guarantee that the synthesized programs actually satisfy the specification that we gave to them. So in order to understand how this can be done, let's have a look at how SuSLik goes about synthesizing programs given their specification. So SuSLik operates in a fragment of a logical fragment called synthetic separation logic. So in SSL, each applied SSL rule transforms a synthesis goal, represented by means of a pre and a post condition, into another synthesis goal and in this process emits a residual program statement. So in order to synthesize a program, SuSLik simply searches through the space of SSL rules and until it can reduce the synthesis goal into a trivial entailment, and in this process also produce the program as a byproduct. Now, in theory, the sequence of SSL rule applications that are used to produce this program should be sufficient to actually build a proof certificate. But interestingly enough, there's a sort of fundamental gap between synthesis and verification proofs that prevents this kind of straightforward translation. So let's have a look at verification proof. In a verification proof, we know the syntax of the program ahead of time. And so we can use the structure of the program to guide our proofs. In particular, we can perform our proofs correspond to a sequence of reasoning rules corresponding to each statement in the program, and these will symbolically execute through the program and incrementally update the precondition. So notice that here, the post condition is left unchanged until the very end, at which point it is actually unified with the symbolically executed precondition Pn. Now, in contrast, when we're looking at program synthesis, we can't rely on the program structure because, in fact, this is exactly what we're deriving in our synthesis procedure. So when we're doing synthesis, each inference rule incrementally transforms the whole synthesis goal and produces program statements as byproducts until we reach a trivial entailment. Now, in particular, make note of the fact that both the pre and post condition can be transformed during each application. And so this brings us to a key problem, which is that when we run into steps in a synthesis goal that transform the post condition, then we need to somehow be able to defer their insight until the end of the proof when we reach this final unification step. So one important question, if we want to do this kind of automated certification, is we need some way of bridging the gap between these two different means of logical reasoning. Another important consideration is the fact that multiple candidate verifiers embedding separation logic in COG are available. For example, we have Hoare Type Theory, or HTT, Verified Software Toolchain, or VST, and Iris, just to name a few. So another important consideration is how we can actually perform the generation of these proof certificates in a uniform way across these different target verifiers. So these two challenges form the basis of our work. Firstly, in order to be able to bridge the gap between these two styles of reasoning, we need some means of interpreting synthesis traces into a verification proof. And secondly, in order to remain verifier agnostic, we need some means, whatever we implement must be some kind of abstract framework that we can instantiate for each target verifier and adjust to its particular idiosyncrasies. So in this work, we implement an abstract proof evaluator framework that is capable of evaluating these synthesis proofs into verification proof certificates. And in order to demonstrate the generality of this technique, we instantiate it for 3 target verifiers, HTT, VST, and Iris. And finally, we evaluate this instantiated framework on a characteristic suite of benchmarks that SuSLik is able to synthesize. And we're able to produce verification certificates for all 3 target verifiers on all benchmarks. So in the rest of this talk, I'm going to provide an overview of how this abstract proof evaluator works, and then we'll conclude by looking at the evaluation. So in order to instantiate our abstract evaluator for a particular target verifier, we need to supply some kind of proof interpretation function. And this will map from logical rules, synthesis rules found in the synthesis proof, into corresponding statements in the proof certificate for our target verifier. Once we've instantiated our framework with such an interpretation function, our evaluator then steps through the synthesis proof and calls the evaluator on each, calls the interpreter on each synthesis rule and produces the corresponding proof certificate. Now I'll explain the two key strategies that we use to bridge the gap between the logical reasoning styles of synthesis and verification proofs. The first is a notion of deferred proof steps that allows the proof interpreter to delay the appearance of a proof step beyond when it is first interpreted. And intuitively, this behaves like a continuation from functional programming. The second component is this notion of proof context that allows a proof interpreter to store and then later retrieve bookkeeping information required in order to produce a valid proof certificate. And the functional programming analog here would be something like an accumulator. So using Hoare Type Theory, I'm going to show how these two features can be used to produce a verification certificate for our earlier list copy example. So on the left, we have the corresponding SuSLik proof tree, and on the right, we have the corresponding proof certificate. So when we're translating between these, certain steps are easy to translate. For example, such as this read rule, SSL rule, and its corresponding HTT counterpart. So in this case, we can simply define our proof interpreter to map from the SSL rule to the corresponding HTT lemma, the application of bind read R. Unfortunately, other steps aren't so straightforward. So if we look at the left branch of the proof trace, of the synthesis trace, you can see that most of these steps are actually in order, up until we reach the close rule, which needs to be deferred to the end of the proof when we reach the unification step. So the close rule operates by unfolding a predicate in the post condition. In this case, it unfolds the second of the two linked lists in the post condition and replaces it with its second constructor. Recall that in a verification proof, any rules that transform the post condition, such as this, have to be performed right at the end. So to solve this, we introduce the notion of deferred proof steps. Rather than emitting the corresponding proof statement immediately, the proof interpreter can choose to enqueue a proof-producing computation onto a queue. This queue is incrementally grows as the evaluator traverses through the synthesis trace and encounters proof steps that modify the post condition. And once it reaches the end of a synthesis proof, these rules are then released. So much like a continuation, this deferred steps allows the proof interpreter to control the ordering of proof steps. Now, if we look closely a bit at the generated rule, we'll see that actually the names of the existential variables that we find in the generated proof are not quite exactly what we need. And the reason here is that when the rule is first enqueued, the SuSLik refers to these existential variables by their default names. However, as the proof continues, we later see rules that unify these existential variables with their true names. For example, here, S prime is unified with S1. Similarly, the other existential variables also get their correct values later on throughout the proof. So to handle this kind of substitution information, we extend the interpreter with an accumulator-style proof context that each invocation of the proof interpreter can choose to update with such bookkeeping information. So let's have a look at this used in our current example. We can instantiate the accumulator and update it with the substitution for S prime and S1. And similarly, each time we encounter another unify rule that updates the unification of these kinds of existential variables, we can add it to our accumulator context. And then by parameterizing our deferred step by this proof context variable, and then invoking it at the end of the proof with the final proof context, we can generate a HTT step that has the correct names for any existential variables. So that concludes the overview of the main strategies that we use to bridge the gap between the two logical reasoning styles of verification and synthesis proofs. In particular, using deferred proof steps that behave like continuations, and proof contexts that act like an accumulator. So now let's, and this concludes the sort of overview of the implementation. We also have to perform some additional proof automation on the Cox side to bridge smaller differences between the reasoning styles of the SuSLik logic and the target verifier. In particular, things to do with the representation of heap predicates, or things to do with how heaplets are framed into and out of function calls. So now let's have a look at our evaluation. When we conducted our evaluation, we wanted to answer two research questions. Firstly, the efficiency of the certification with regards to proof size and checking time. And secondly, any kinds of design choices for the synthesizer or the verifier that might complicate the process of automatically generating these proof certificates. So to evaluate the efficiency of the certification, we evaluated our instantiated framework for a characteristic suite of 15 benchmark programs that SuSLik can synthesize. And the statistics of these proofs are presented on screen. So in particular, if we look at the proof sizes, you can see that they are all fairly reasonable. Most of the proofs are fewer than 100 lines. So even though they are machine generated, they aren't too hard to read. The specifications are all less than 100 lines. And for HTT and Iris, the proof checking times are all reasonably manageable, all being within 2 and 20 seconds, and the few cases where it goes above that being below a minute at most, or below a minute and a bit at most. VST is an exception here, taking significantly longer, and the reason for this is that VST provides, or the main way of reasoning about heap unification in VST is through this automation tactic, entailer. And entailer is capable of is a fairly powerful automation tactic, but it comes with a certain degree of performance overhead. And and our generated proofs rely quite heavily on entailer, hence the increased proof checking time. So for the second question, we identified two key challenges that complicate the process of automated certification. The first challenge is any kind of design choices in the implementation of the target verifiers that can complicate the process of bridging the gap between SuSLik and the target logic. So to understand this, let's have a look at our implementation experience for the 3 target verifiers. So let's have a look at HTT. In fact, we had the easiest time working with HTT, in particular because of its shallow embedding. And this was useful because it made things like writing tactic automation to bridge smaller gaps between the reasoning styles of HTT and SuSLik easier. And there were more places where things were similar between them. For example, in HTT proofs, there's no need to distinguish between program and proof terms. A pure expression in an HTT program is a Galena function that can be represented equivalently in the corresponding proof context. This isn't the case for the other verifiers we used, such as VST and Iris. Now, for VST, this is a notable backend because it is the only one that targets machine executable real-world C programs. And so VST tackling real-world programs comes with a certain a suite of powerful automation that intended to make reasoning about its complex representation easier. However, interestingly enough, this didn't always make things easy for us. So in particular, VST provides a suite of notations to make its proof context simplify its proof context and make understanding proofs easier. However, this actually made things more difficult for us because if we wanted to write any kind of automation to bridge the gap between VST proofs and our and SuSLik proofs, then we had to actually delve into the implementation details beneath the notations and actually reason about the underlying structure of the proof context. And this made our corresponding tactics and proof automation more fragile and more likely to break. Now, our experience with Iris was that it was the most difficult backend to produce proof certificates for. And the key reason for this is that Iris uses a human-guided approach to reasoning, in which the prover has to explicitly name and pass in respective heaplets into sort of any function calls and do the framing manually. And this isn't something that SuSLik relies on, because SuSLik does all of its proofs mainly by heap unification. So there is no explicit naming of heaplets. In order to bridge this gap, we introduced an additional set of automation on top of Iris that relies more heavily on heap unification to avoid this kind of error, this kind of discrepancy between the proof styles. But because possibly due to our inexperience with Iris itself, we found the tactics that Iris provides made our automation somewhat fragile, and we had to be fairly careful to make sure that the proofs were tractable, even with the additional benefit that we gained by having a proof context. So the second challenge that we identified was in recreating any synthesis steps that are not recoverable from the synthesis proof. So in particular, separation logic is not particularly good at handling pure entailments. And for this reason, SuSLik actually attempts to dispatch any pure entailments by means of querying an SMT solver such as Z3 to check whether the entailment holds. Unfortunately, when we're generating a proof certificate, we need a constructive proof of any such facts. And these can't be generated from the simple yes or no answers that an SMT solver can provide. So to match the oracular insight of an SMT solver, we turn to certified solvers, or hammers as they're referred to. A hammer is a single line command that provides access to powerful automation, and internally it calls out to some kind of automated theorem prover to perform some kind of proof search using the available lemmas in the proof context. So in our case, whenever we found a pure entailment in the synthesis proof, we would extract and pre-print it as an external lemma, and then we would attempt to dispatch the lemma automatically using Cockhammer, a certified solver. These additional auxiliary lemmas would then be included into the proof script as hints, where they could then be used by the automation transparently during the main proof. So as a stretch goal for HCT, we also verified a number of additional more complex examples that relied on such oracular insight from SMT solvers. And in all of these cases, provided the auxiliary lemmas were included in the context, the main proof was able to go through without any additional work. Additionally, for the auxiliary lemmas, we were able to dispatch a majority of them by using Cockhammer. And for the cases where we were not able to, this only required some small additional bookkeeping to make the proofs go through. So the overall effort in generating the verification certificate was fairly minimal. So in the future, it would also be interesting to investigate a middle ground between fully automated and more human-in-the-loop automated certification of programs. So to summarize, we were investigating how to bridge this fundamental gap between synthesis and verification proofs. In order to do this, we built an abstract proof evaluator framework that can evaluate a synthesis proof into a verification, into a proof certificate by means of techniques inspired by continuations and accumulators. We instantiated this framework for 3 target verifiers, HCT, VST, and Iris, and we evaluated this framework on a suite of characteristic benchmarks, 15 programs in total shared by all verifiers, plus some additional ones for HTT. And with that, we were able to achieve fully automated, fully certified program synthesis. So thank you for listening. Pleased to take any questions.
So are there any questions? Yeah. Maybe come out because there's a mic. Yeah.
Oh, maybe this. Oh.
No, this one because there is a mic problem. Yeah.
So SuSLik generates like OCaml programs, but VST tries to operate on C programs. Do you have any problems with sort of like redefining the semantics of those two languages?
So actually, SuSLik doesn't generate OCaml programs. It generates SuSLang programs, so a custom sort of C-like, custom language. So actually, its semantics is, is quite close to C already. There were some minor differences that we had to make use of. For example, SuSLik assumes the existence of sort of free, being able to allocate memory without errors. And in our case, C, malloc may fail. So we had to sort of axiomatize a version of malloc that couldn't fail.
Are there some questions in the chat room? We have some questions. So somehow you're trying, the fact that you're trying to synthesize programs out of separation logic makes me think about the Curie-Howard correspondence, where you try to synthesize a program to prove the proof of some types. So I was wondering if there is some connection between the two, especially as you're using coq.
So in this work, as far as I think about it, there's no direct correspondence to Curie-Howard. Although we have some other work that's currently under publication, which does rely on the Curie-Howard correspondence when applied to a program to separation logic-based proofs. In particular, because these languages are deeply embedded, there's not a direct correspondence one-to-one between the proof and the corresponding C program, but there are notions. There are ways of utilizing the information within the proof to sort of gain additional information about the generated programs. And we've been using that for things like automated proof repair and maybe optimization in the future. Yes.
Great. You want to comment? Oh, I will read it. Okay.
So when you say you applied your proofs to these three tools, isn't Iris a framework where you can embed languages? Did you do it for certain embedding or?
Yes. Thanks for the question. So in our case, we targeted sort of that's a great question. We targeted Heap, which is Iris's sort of default logic. I guess the true way of performing this would actually be to embed SuSLik's semantics into Iris, like encode SuSLang as an Iris embedding. Although at the time we lacked the sort of domain knowledge to do that effectively, so we chose the simplest option.
Tiny other follow-up question is there's an embedding of a subset of C in Iris, so did you consider just using that as well as a maybe slightly fairer comparison between how much effort it is with VST and Iris? So
just to answer that question, I think the difficulty that we encountered with Iris wasn't particularly to do with discrepancies between the semantics. So I think, yes, you're right, that it would have been a slightly fairer comparison if we compared the actual implementation of C semantics in Iris. But the sort of proof style itself would remain the same, and we would probably run into the same issues with Heap-Manipulating.
Yeah, I can add some more, because I worked on the Iris. So, yeah, the issues weren't really so much the difference in semantics, although we do have a slightly modified version of
Yes.
but slightly different, more like C. The issue was more around Iris proof mode, and that it kind of forces you to manually manage hypotheses and manage the context. And we had to write some tactics on top of Iris proof mode to no longer require that.
Let's take a picture again.